Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. Title of today's lecture is Free Convection between two vertical plates. So, till now whatever the isothermal flow of non-Newtonian fluids when we have studied in different geometries, primarily we have made use of a continuity equation, momentum equation, and then by using some mathematical procedures we tried to obtain velocity profile, then volumetric flow rate, then friction factor, etc. That is what we have seen. Right. So, but if you have a non-isothermal flow of non-Newtonian fluids, then what are the additional things you may be requiring? Obviously, when the system is at non-isothermal conditions, so then you may require more additional information. Something like, let us say, in a given condition, if the viscosity of fluid is changing, is varying with respect to the temperature, so that additional information is required, which we have not considered till now. Right. Sometimes let us say if there is a density variation because of the temperature changes because of the non-isothermality of the system, then so those associated changes in the density with respect to temperature should also be encountered, should also be incorporated in the system. Then obviously energy equation must be coming into the picture because the system is at non-isothermal conditions. So, that is the additional thing is required. So, then sometimes we also require something like caloric equations of state, etc. Those kind of information are also required. So, before getting into the more details of non-isothermal flow of non-Newtonian fluids, we make a list of things that are required in general in order to study this non-isothermal flow of non-Newtonian fluids. So, what are the things are required? Whether it is isothermal system or non-isothermal system, in the transport phenomena, definitely we need continuity equation or equation of continuity. Then equation of motion, that is required because if the non-isothermal flow, we are talking about non-isothermal flow, we are not just talking about the conduction where there is no flow, etc. We are also taking incorporation, we are also taking the information of the flow of non-Newtonian fluid. So, then if the flow is involved, so then equation of motion definitely would be there. Then equation of energy, because the system at non-isothermal condition, so definitely we need to know how the energy is changing with respect to the space and time. So, that is the reason equation of energy is also required. Then thermal equation of state, the P function of rho T, etc. Then caloric equation of state, Cp tilde function of rho T, etc. Then for density and then temperature dependence, viscosity and thermal conductivity, how it is dependent on temperature, etc. Those information, those equations are also required. And then obviously the rheological model of non-Newtonian fluid is definitely is required, whether the flow is isothermal or non-isothermal. If we are anticipating that material is having non-Newtonian behavior, so then that rheological model information must be had, so that in order to solve these problems. Then obviously boundary conditions and then initial conditions are also required if we are solving for the time dependence as well. Okay. So, now here so majority of them are not required for all the problems in general, but many of them are definitely required. So, what happens, let us say if you are incorporating all the information, how the velocity is changing with respect to the space and time, how the temperature is changing with respect to space and time, similarly pressure distribution, density distribution, etc. If you wanted to know all of these things, so definitely all these things should be incorporated in the solver, and then when you incorporate all this information, then analytically solving such problems becomes relatively impossible. So, then we have to go for numerical solutions. Even for the isothermal systems, if you do not if you have the dependence of velocity on more than one variable, then it becomes very difficult. So, now at least in the velocity case, in the flow cases, isothermal flow cases, we can say that velocity is function of only y or only z, those kind of thing, or velocity is function of r, etc. Those information we can say, we can deduce from the the basic problem statement. But for majority of the cases, the temperature you cannot say whether it is function of only y, function of only z. It must be explicitly mentioned, or otherwise you have to you may be solving the temperature function of both y and z. Let us say flow through pipes, when we have taken Vz is function of r, that is what we have taken, and then accordingly constraints we have listed out, and then we solve the problem for Vz as function of r, right. But the same pipe flow, if the the flow is at non-isothermal conditions, then temperature you cannot say it is function of r only, it will also be function of z, even though velocity is function of r only. Vz, even if Vz is function of r, temperature you cannot say it is function of r only, it will also be function of z in the case of pipe flow, if the system is at non-isothermal conditions. Okay. So, those are the additional problems are there, right. So, obviously, now what we understand, more equations are coming, more constraints are coming, the solving heat transfer problems are solving non-isothermal flow problems, that is where flow is also involved. It is not just temperature variations are there and there is no flow, it is not like that. So, when there is a flow also there and then temperature variations are there, so that is non-isothermal flow conditions are there, the solving problems is going to be relatively difficult compared to the isothermal flow of non-Newtonian fluids what we had seen in till now. Okay. However, for any problem as engineering students, we can list out the constraints and then we can make the problems as simpler as possible, but not going far away from the reality, still maintaining not exactly the reality, but close to the reality. We can solve the problems by making certain kind of assumptions as engineering students. So, that is what we are going to do in the case of this non-isothermal flow of non-Newtonian fluids in coming few lectures. So, as I mentioned, the entire set of equations whatever we listed in the previous slide, if you wanted to solve, so then you have to depend on the numerical simulations. However, prior to solve the problems numerically, it is a good idea to have a restricted solutions in the sense under certain kind of constraints, like like momentum transfer, we have listed out some constraints like steady, isothermal, and then symmetric, fully developed flow, etc. Those kind of constraints, under those constraints we have solved problems. Likewise, in this case of non-isothermal flows of any system also, if you make some kind of constraints, so you are going to have certain advantages, like making order of magnitude analysis. So, and then are investigating limiting cases, something like that, those things you can see. What does it mean by, let us say, even for example, getting back to our viscoelastic behavior, when a same viscoelastic fluid is flowing through a packed bed of a particle of different sizes. So, then we have seen under such one conditions of particle size, the viscoelasticity is not necessary to consider. That is what mean by this order of magnitude analysis. Such kind of analysis we can do here also in the case of non-isothermal flow. Let us say the Reynolds number is very small, right, but the Prandtl number or Peclet number is very large. So, then we can apply something like a thermal boundary analysis and then simplify the problem and then find out the required temperature distribution, etc. Those things we can do, right. So, limiting cases also. So, like order of magnitude limiting cases, like you will come to know whether is it really important to incorporate all the information, all the equations that we have taken, etc. Let us say if you have taken the flow through pipes, right, vertical pipe, is it really important to have the convection effect or free convection effect? That those kind of analysis we can do by having the restricted solutions. How we go problem to problem, right? And then this can be done by obviously making some standard assumptions. Some of the standard assumptions which are very common to the non-isothermal systems, heat flux is 0, right. Like in the momentum transfer, we can say the shear stress is 0 at a given location, those kind of constraints. Another constraint is that constant physical properties. So, constant physical properties, 0 fluxes may be useful in many of the cases as a standard assumptions. Some examples where we can have in general 0 fluxes case are adiabatic flow processes in systems designated to minimize frictional effects, like in venturimeters and turbines. Then high speed flows around streamlined objects, etc. So, these are some kind of examples we can have. So, that is a very generalized introduction about non-isothermal flows, what we need to have, how should we proceed kind of thing, right. So, now what we start with a free convection problem between two vertical plates, right. So, here non-isothermality is there in the system, but we are not solving only temperature distribution, but that temperature distribution we utilize to find out how it is affecting the density, and then that change in density, how it is it causing a convection, and then because of that free convection how the velocity distribution is changing. That is what we are going to see. Basically we are going to find out here also the velocity distribution, but now the velocity distribution is also affected by the non-isothermality of the system because of the free convection existing in the system. Okay. So, free convection usually for that purpose we use the Bosnick's equation of motion for forced and free convection, so that we can say under which conditions forced convection is dominating, under which conditions free convection is dominating, that is what we can understand. So, since we are starting with the free convection problem, so we see a few details about the Bosnick's approximation. So, equation of motion derived previously are valid for isothermal and non-isothermal flows as well, that we have already mentioned while deriving the equations. Okay, irrespective of the nature of the flow, irrespective of the nature of the fluid, generalized momentum equations we have developed. So, in non-isothermal flow, fluid density and viscosity may depend on temperature and pressure. So, in is it depending both on temperature and pressure? Or both density and then viscosity are dependent on this temperature and pressure, or only density is depending on the temperature but not depending on pressure. All these constraints of the problem one should have. Okay. So, variation in density is important as it gives rise to buoyant forces and thus to free convection. Whatever the density variations are there because of the temperature differences, what happens that buoyant forces cause a change in the velocity distributions. How is it going to change in the velocity distribution? That has to be discussed specific to problem. So, we are going to discuss one problem today. So, density variation with respect to temperature can be approximated by Bosnick's approximation, and then it is given by these things. Rho at temperature T is equals to rho bar minus rho bar beta bar T minus T bar. So, whatever the bar are there, so that indicates evaluated at reference temperature T bar. Okay. So, rho bar is nothing but density at temperature T bar, okay. And then beta bar is nothing but coefficient of volume expansion at constant pressure but temperature T bar. So, that is beta bar is equals to minus 1 by rho bar dou rho by dou T, right. So, this rho bar is at temperature T bar, and then this rho how it is changing with respect to temperature at constant pressure, this first derivative from here we can get it. Okay. So, how do we get this equation? So, let us say density dou rho by dou T whatever is there, that if you do the Taylor series expansion at constant pressure, then dou rho by dou T is equals to rho at T minus rho at T bar divided by T minus T bar. So, that means if T minus T bar, if you take to the left hand side, T minus T bar multiplied by dou rho by dou T is equals to rho minus rho bar. Rho at T bar we can call it rho bar. So, that means from this beta bar definition, what we can have in place of dou rho by dou T, we can have minus rho bar beta bar. So, left hand side minus rho bar beta bar multiplied by T minus T bar is equals to rho minus rho bar. So, that means rho is equals to rho bar minus rho bar beta bar T minus T bar. Okay. So, this equation is giving you how the density is varying with respect to the temperature by taking a reference temperature T bar. Okay. By substituting this equation in rho g term of equation of motion, then what we get? This is the generalized equation of motion that we have seen in vectorial form. We have written rho capital dV by dt is equals to minus del p minus del tau plus rho g was there. In place of plus rho g, now we are writing in place of rho what we are writing? Rho bar minus rho bar beta bar T minus T bar, and then this entire thing is being multiplied by G. So, whatever rho bar G is there from here, rho bar G is combined with the pressure term and then written here, and then remaining minus rho bar G beta bar T minus T bar is written as additional term. So, this term is buoyant term. Okay. So, in LHS of this equation here in place of rho we are not writing this Bosnick's approximation, because it is valid for bands terms only, but however in some cases like very high flow rates, there also like supersonic flows etc. In such conditions also, if the velocity in such conditions also if the density is varying with respect to temperature in such kind of high flows, then also in the left hand side we have to do we have to apply such kind of approximation. But for the time being, for our chemical engineering problems, we are not doing it. We are doing that replacing rho by rho bar minus rho bar beta bar T minus T bar only in the right hand side term in place of rho G term. Okay. There only we are doing it. So, the previous equation whatever we have seen describes two limiting cases of forced and free convection and the region between these two limiting cases. What does it mean by? If it is forced convection is dominated, so then last term whatever is there, that can be neglected. Okay, in relation to the or in comparison to the other term. If it is free convection is dominating in the problem, then what we can see, whatever this minus del p plus rho g minus del p plus rho bar g term can be neglected in comparison to the other term of free convection buoyant term. Okay. So, this kind of analysis we can have. So, in forced convection buoyant term, that is minus rho bar G beta bar T minus T bar is negligible. In free convection, term minus del P plus rho bar G is small, and usually omitting it is not going to affect the solution much. And then in general some examples where we can omit this minus delta P plus rho bar G, despite of which the solution is not going to be affected much. So, those examples are vertical rectilinear flow and flow near submerged objects in large bodies of fluid etc. Then setting minus delta P plus rho bar G equal to 0 means that pressure distribution is same as that of fluid at rest. Whatever the hydrostatic pressures are there, so that is the pressure distribution is same to that hydrostatic pressure. Okay. So, that is what it mean by if you are setting up, if you are taking minus delta P plus rho bar G equal to 0, that means pressure distribution is same as that for the fluid at rest, because this rho bar G is nothing but something like H rho G, that hydrostatic pressure etc., those kind of terms. So, that is what it mean by. Okay. So, replacing rho on LHS of equation of motion by rho bar has been successful for free convection at moderate temperature differences. Under these conditions, fluid motion is slow and acceleration term d v by dt is smaller compared to the gravity term in equation of motion in general. And then for systems where acceleration is also large with respect to g, one must also use Bosnick's approximation on LHS of equation of motion. Some examples like gas turbines, near hypersonic missiles etc. Okay. So, but for most of the chemical engineering problems, we do not need to worry about applying the Bosnick's approximation in the left hand side density term of equation of motion. So, now coming to the problem that we are going to solve. Laminar free convection flow between two vertical plates at different temperatures. So, schematically if you see, we have taken two vertical plates, okay, which are long enough that you can say that end effects are negligible. These two plates are separated at distance 2b. Okay. Coordinate system is taken such a way that the y is equals to 0 is in between these two plates. Horizontal axis is y axis, vertical axis is z axis. So, one of the plate is located at y is equals to minus b, another plate is located at y is equals to plus b. and then gap between these two is 2b. So, the heated plate is at y is equals to minus b, and then corresponding temperature is T2 as given here, shown here, and then cooled plate temperature is maintained at T1 as shown here. Now, what happens in this problem, the velocity distribution, what is this velocity distribution, that we have to find out. Okay. Just pictorially it is shown like parabolic profile like that, but it may not be true. Okay. So, we have to derive it. So, now in this problem we are talking about the free convection, laminar free convection flow. What happens here? That means free convection is taking place, that means the variations in density are taking place because of the temperature variations. Further to mention, these plates are closed both at the top and bottom. This is closed at the both at the top and bottom, right. So, that whatever the fluid is there, so that is circulating because of the convection only. That means, whatever the fluid elements are there towards the heated plate, their density is decreasing because of the higher temperature, and then since the fluid molecules density is decreasing, the fluid molecules are rising towards the heated plate, and then towards the cold plate the temperature of the fluid elements are less. So, then density is decreasing. So, then the so called the fluid elements or the fluid layers towards the wall are having the decreasing velocity. And then because of this temperature difference, that is T2 minus T1 is maintained here. So, because of that one, that temperature difference is causing density variations, and then that density variation is causing buoyant forces within the system, and then because of that buoyant force, this material is circulating, the fluid is circulating, it is raising towards the left wall and it is falling towards the right wall, because left wall is heated plate and then right wall is cold plate. So, this circulation is continuously taking place, okay, because both the top and bottom of the system are closed, right. Now, for this case, how this Vz is changing? So, if it is isothermal condition, so then we can solve the way that we have solved by simply simplifying the continuity and then momentum equations, and then one of the momentum equation would be giving expression for tau yz, and then tau yz for the given fluid nature, if you substitute power law or Newtonian or Bingham plastic, and then integrate it, apply the boundary condition, get the velocity profile, that is done. But in this case, we have to follow the similar approach, but in addition to that, we should also consider how this rho is changing with respect to temperature, and then that change in rho should be brought into the equation of motion in the right hand side term, where rho g term is there. Okay. So, whatever the listed out details of figure are given here, fluid of density rho and then viscosity mu is located between two vertical walls at 2b distance. For the simplicity, we are taking as a first problem only Newtonian fluid, okay, so that we can solve the problem easily for the time being, because it is the first problem on non-isothermal flow of fluids. Okay. So, temperature at heated wall is T2 at y is equals to minus b, temperature of cooled wall is T1 at y is equals to plus b. Assume delta T is very small, so that terms containing delta T square, delta T cube, etc. are negligible. If delta T itself is very small, so then their square cube terms would also be very small, so that we can neglect them. And then temperature gradient causes fluid near hot wall to rise and descend near cold wall. System is closed at top and bottom, so that the fluid is circulating between the plates. Mass rates of flow of fluid in upward moving stream is same as in downward moving stream. So, that means let us say between y is equals to minus b to y is equals to 0, fluid is rising. Whatever the rate it is rising, the same rise at the same rate it is falling in the region y is equals to 0 to y is equals to plus b. Okay. So, that is fluid rising rate is equals to fluid falling rate in this system. So, plates are tall enough to avoid end effects, so that we can have the fully developed flow assumptions, and then temperature is function of y alone. It is given. It is given, so we do not need to worry about this, that temperature is function of y or z, because for the temperature, not only just for the temperature, in general for any of the scalars, it is difficult to say whether it is function of only one coordinate, it is not function of other coordinates, like that it is very difficult to say. Since in the problem statement it is given, so we do not need to worry. So, the temperature variations are required, or the temperature distribution we should understand, because that information is required to substitute in Bosniak's approximation that we are going to apply for the right hand side rho term. Okay. So, what are the constraints in general? We have such kind of problems. We have steady state, laminar flow, it is already mentioned in the problem statement. Okay. And then plates are tall enough, so end effects may be avoided, that is what it mentions. So, fully developed flow we can have, right. And then Vz component is only existing, and then it is function of y. Temperature, from schematic we do not understand whether it is function of y alone or z also, but however luckily it is given in the problem that it is function of y only. So, need not to worry about that one. So, these kind of assumptions we are having. So, Vx is 0, Vy is 0, and then t is not function of z and then x. Okay. So, under these constraints what we do, we first obtain the temperature distribution, and then we use the temperature distribution in equation of motion to find out the velocity distribution for this free convection problem. So, equation of change for non-isothermal system in Cartesian coordinate systems, we have rho Cp tilde dou t by dou t plus Vx dou t by dou x plus Vy dou t by dou y plus Vz dou t by dou z is equals to k dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square. This is we derived in week 3 or 4 of the course, right. So, now here steady state, so the first term is 0, Vx is negligible, Vy is also negligible, Vz is existing, but the temperature is not function of z, it is function of y only. That way you can cancel out. Let us say if that information is also not given, so we retain it. Okay. Then temperature is not function of x, temperature is not function of z. So, we have dou square t by dou y square term only in the right hand side. So, rho Cp Vz dou t by dou z is equals to k dou square t by dou y square. So, now from here this term can be cancelled out based on two constraints. One is that temperature is not function of z, that is given, but from the physics of the problem, the convection whatever is there, that is there in the y direction, right, or the convection whatever is shown in the z direction, that is very less compared to the conduction in the y direction. So, by that constraint also we can have that convection in z direction is very small compared to conduction in y direction. So, then we can have k dou square t by dou y square is equals to 0, and then when you integrate you get t is equals to C1y plus C2. We have two boundary conditions, t is equals to T2 at y is equals to minus b, and then t is equals to T1 at y is equals to plus b. So, we have these two equations, two unknowns C1, C2, so we can find out them. So, now if you add them together, what will happen? C2 is equals to 1 by 2 T1 plus T2. Now, this C2 if you substitute here, then you can get C1. So, T is equals to C1y plus 1 by 2 T1 plus T2. Now, this first boundary condition we have at y is equals to minus b, T is equals to T2. So, T2 is equals to C1 minus b plus C2, C2 is 1 by 2 T1 plus T2. So, from here if you do the simplification, right. So, then what we will have? Left hand side we have all these temperature terms, right hand side C1 minus b we are keeping, right. So, then this T2 minus half T2 is plus half T2. So, plus half T2 minus half T1 is nothing but C1 minus b. So, from here C1 is equals to T2 minus T1 by 2 minus b, right. So, T2 minus T1 we are writing delta T, right, I am not writing this one delta t divided by minus 2b. So, let us keep it as it is. Okay. There is a reason for simplification later on. So, C1 is equals to delta t by 2 minus b, 2 multiplied by minus b. Now, we have both C1 and then C2. This is nothing but C2. This C1, C2, if you substitute in this equation, t is equals to C1y plus C2, then we get this equation. T is equals to C1, C1 is nothing but delta t by 2 multiplied by minus b, C1 y, and then y plus C2 is nothing but T1 plus T2 by 2, that we are calling T bar, average temperature. Okay. So, this is what we are having. So, that means T, we can write T is equals to T bar minus 1 by 2 delta T y by b. So, what we understand here, T is a linear function of y, that is what we understand. Before solving the problem, from the problem schematic, we do not have any information whether it is linear or non-linear, etc. So, now by simplifying this equation of energy and then applying the boundary conditions, we understand the temperature is a linear function of y. Fine. So, temperature distribution is known. So, now what we do? We simplify the equations of motion, right, different components of equation of motion. So, start with the z component. Z component equation of motion in Cartesian coordinate is this one. So, what we have here, steady state, this term is 0, Vx is 0, Vy is 0, and then Vz is not function of z, it is function of y only, or by fully developed flow also dou Vz by dou z is equals to 0, because plates are long enough so that end effects are negligible, that is given in the problem statement. The pressure in general we do not know anything, so keep it as it is, and then this Vz is not function of x, it is not function of z, so it is function of y, so then we have to retain this thing, and then in the z direction is vertical, z direction, z coordinate is in the vertical direction, so then gz is there. Okay. So, what we get, mu dou square Vz by dou y square is equals to dou p by dou z minus rho gz. Now, g is acting in the negative z direction, so gz is nothing but minus g. So, we have this equation, mu dou square Vz by dou y square is equals to dou p by dou z plus rho g. So, let us keep it as it is, not solving this problem, this equation as of now, because this pressure is function of z, that is what we are understanding from this equation. Now, if you integrate this equation, so you should know whether it is function of y or not. If it is function of y also, then integration become complicated. So, we should understand whether the pressure is a function of y or not, especially before solving this differential equation for Vz, right. So, if you wanted to know this one, what you have to do? You have to simplify the y component of equation of motion. So, that is what we are going to do. Similarly, if it is pressure is function of x or not, that if you wanted to know, you have to simplify x component of equation of motion. So, if we find that p is not function of y, so then this integration will become easy, and then we can straightforward do the integration by assuming the right hand side terms are constant with respect to y. But that also we cannot do directly, because now here rho is function of t and then t function of y. So, that also we have to substitute here as per the Bosenick's approximation. So, those steps we are going to do subsequently. So, y component of equation of motion is given here. So, steady state, this term is 0, Vx is not there, Vy is not there, Vy is not there. So, left hand side all the terms are negligible, pressure we do not know, Vy is 0, so all these 3 terms are 0, and then in the horizontal direction gravity is not there, y direction is horizontal direction. So, what we understand, dou p by dou y is equals to 0, that means pressure is not function of y. So, at least we are not worried about dou p by dou z term in equation number 4, to integrate it and then get the velocity profile. Okay. So, now next is x component of equation of motion, that is given here. So, we have steady state problem. So, first term is 0, Vx is 0, Vy is 0, and then Vx is 0. So, here also left hand side terms, all terms are negligible, and then Vx is 0, and then in the and then gravity is only in the z direction. So, Gx is also 0. So, here also we get dou p by dou x is equals to 0, that means pressure is not function of x. Now, what we understand, delta t is very small here, that is what we assume. So, that delta t square delta t cube we can neglect. Thus, density changes in the system will be small, and then this suggests that rho should be expanded in Taylor series about reference temperature T bar, which is the average temperature of T1, T2. Then according to this Taylor series expansion, rho is equals to rho at reference temperature T bar plus d rho by dt at reference temperature T bar multiplied by T minus T bar, that is what we have, and then so on. So, delta T square term, delta T cube terms would be there. So, we are not considering it. So, this we can write rho at T bar is nothing but rho bar. So, this d rho by dt we already understand that it is minus rho bar beta bar, that is what we understand from the definition of volume expansion coefficient or coefficient of volume expansion for a given fluid at constant pressure, right. So, that is we are evaluating at T bar temperature, right. So, beta is coefficient of volume expansion at T bar. So, then beta bar we can have. So, this beta bar definition of coefficient of volume expansion is nothing but 1 by V dou V by dou T at constant P. So, V we are writing 1 by rho bar, because this V whatever is there, this is for the volume, and then this is at the reference temperature T bar. So, in place of V we can write 1 by rho, and then that also at reference temperature rho bar. So, that is what we have done, and then we can integrate, then we can differentiate this one. So, we get minus 1 by rho bar dou rho by dou T at constant P. This is not, there is no bar here, there should not be bar because rho bar is a constant value, dou rho by dou T at constant P. So, this if you substitute in equation number 4 in place of rho g, rho should be replaced by rho bar minus rho bar beta bar T minus T bar. So, then this equation we get. Now, this equation we have to integrate to get the velocity distribution. So, before that we should also substitute what is this T, that also we do subsequently. Okay. So, now here this equation gives a balance amongst different forces. This force indicate viscous force, this term gives the pressure distribution pressure force, and then this term gives the hydrostatic pressure terms, and then this gives the buoyance force. So, balance amongst viscous, pressure, gravity and buoyance forces are given by this particular equation. Now, we have already derived temperature by simplifying the energy equation, that we got T is equals to T bar minus half delta T y by B. This is our equation number 3 in previous slides. This equation number 3 we are substituting our just derived equation number 9. So, this is equation number 9, in place of T we are going to use this equation now. So, when you use it, so what you get, right hand side term T minus T bar you can write minus half delta T y by B. So, this term would be plus half rho bar G beta bar delta T y by B. So, now in the right hand side, except this y, all other terms are independent of y. So, we can integrate without any difficulty, right. Before integrating, what we do, we take this mu to the right hand side. So, we need boundary conditions at y, at both the walls. Because of the no slip conditions, we have the velocity 0, right. Whether it is y is equals to minus b or y is equals to plus b, the velocity is 0 because of the no slip conditions, right. Okay. So, this equation when you integrate, you will get two constants. So, we have two boundary conditions. So, there should not be any difficulty in obtaining the constants also. On integrating this equation, we get this particular term, that before integrating, first I have taken mu to the right hand side. So, it is coming under the denominator term, right. Then after first derivative, what I get here, first term is multiplied by y, and then second term y is there. So, y square by 2 plus 1 constant, once again integrating, what I get, Vz is equals to, this term is as it is, 1 by mu dou p by dou z plus rho bar g, and then y, integration of y is y square by 2. Now here integration of y square is y cube by 3, and then C1y plus C2. So this is the equation we have rewritten once again. Okay. Now applying the boundary condition, at y is equals to minus b, Vz is equals to 0. So wherever y is there, we are writing minus b, so b square here, and then minus b cube here, and then minus b here. Another boundary condition, at y is equals to plus b also, Vz is equals to 0. So in equation number 12, wherever y is there, we can substitute plus b, so plus b square plus b cube plus b here. Now these two equations, if you add together, what will happen? So these term are same, so we can cancel out. This term are same, but different signs, so we can cancel out. So C2, 2C2, and then 2 times of this term, that is b square by mu dou p by dou z plus rho bar g. Right. So from here C2 you get this expression. This C2 we are going to substitute here to get this C1. So in that equation number 12a, this is 12a, in place of C2 we are writing this C2 constant that we just obtained, then simplify it, then you will get C1 is equals to this constant. Now this both C1, C2 you substitute in equation number 12, so then you have this expression. Next step, what you do from this term, and then from this term what you do, you try to take b square common. What you try to do, b square if you take common, rho bar g beta bar delta t by 12 mu b square multiplied by y by b whole cube minus y by b you will get. And then from these two terms, b square by 2 mu dou p by dou z plus rho bar g if you take common, then you get y by b whole square minus 1 as the multiplication factor. So this is the velocity profile. Okay. So now this velocity profile, rho bar, that is density at reference temperature T bar is known, beta bar for a given system might be available or must be given, delta T is known, viscosity is known, width of or gap between two plates is known, everything is known except this dou p by dou z. If you know this dou p by dou z, then you can know the velocity profile easily. So now still this is the final velocity distribution equation. So we do not know what is dou p by dou z, so we cannot use it for a final applications. So now we try to obtain what it is. From the problem statement, it is given the rate at which fluid is rising, the same rate it is falling. That means if you take for the both the limits of y is equals to minus b to y is equals to plus b, integral of rho bar vz dy should be 0, right, and then rho bar is constant, so that also you can take to the right hand side. So integral minus b2 plus b vz dy is equals to 0. If you do, then you can get some kind of information about this dou p by dou z. So vz, just now we derived this equation. Now this equation we substitute here and then integrate it. When you integrate here, the first term, these are the constant, in place of y cube, integration of y cube is y power 4 by 4, integration of y is y square by 2, and then second term this is constant. So integration of y square is y cube by 3, and then integration of constant 1 is y. Limits minus b2 plus b, if you substitute, first term rho bar g beta bar delta t b square by 12 mu is as it is. Then when you substitute these limits, you get upper limit these two terms, lower limits these two terms. What you can understand, these two terms are same but opposite signs. Similarly these two terms are also same but opposite sign, so we can cancel out. The second term, b square by 2 mu dou p by dou z plus rho bar g, and then this is the upper limit after substitution, this is the lower limit after substitution, right. So now altogether in these two terms, first term is anyway 0 because whatever the terms that are being multiplied, so that is all 0. So, first term is 0, second term whatever this summation comes out, we can write simply take it to the right hand side, and we can write this way. So, what we can get, dou p by dou z is equals to minus rho bar g. That means dou p by dou z plus rho bar g is equals to 0. So, that means in this equation the second term is 0. So, in the velocity profile we need only this first term, because dou p by dou z plus rho bar g is equals to 0, that we understand from this statement of the problem. So, therefore, Vz would be only the first term of equation number 12 that we have derived previously. Only first term of velocity distribution should be taken under consideration, because second term is having dou p by dou z plus rho bar g, which is 0. So, second term of that velocity distribution equation is 0. So, we have only first term in the equation. So, then velocity profile is this one. So, before winding the class, if you wanted to have the average velocity in the upward moving stream, so average velocity only in the upward moving stream. Upward moving stream is between y is equals to minus b to y is equals to 0. So, integral minus b to 0 Vz dy divided by b, if you do, you get the average velocity in the upward moving stream. So, when you do it, this Vz is equals to, Vz average is equals to this all term divided by b, and then integration of these terms. So, integration of y cube is y power 4 by 4, and then integration of y is, and then integration of y is y square by 2, limits minus b to 0. When you substitute and then simplify, you get Vz average is rho bar g beta bar delta t b square by 48 mu. Okay. This is how we have to solve non-isothermal flow of any fluid, whether Newtonian or non-Newtonian. So, we have taken simple Newtonian fluid in this today's lecture. So, we will be taking different non-Newtonian fluids and then more complicated geometries in the coming lectures. Reference: these details have been taken by the standard book Transport Phenomena by Bird, Stewart and then Lightfoot. Other useful references are provided here. Thank you.